Hello everyone, thank you for the introduction. So today I'm going to discuss a temperature sensor, and the key material is the praseodymium manganese oxide, and so we'll see how this device could replace the conventional frequency to digital smart temperature sensors as they are known. So I'll go through the device first, the fabrication, characterization, and then we'll talk about the circuit implementation of the sensor and the output characteristics, and finally I'll conclude. So the motivation is something like this. So if you look at the circuit of a conventional ring oscillator with the current starved bias currents here, so we can control the frequency of this ring oscillator by changing the currents here. And if this current could be made temperature dependent properties of the MOSFETs, if they control the bias of these current starved ring oscillator, so we directly get a count or a frequency output from the temperature input. So this is the kind of circuit which is used in an ADC-less implementation, where you don't need to convert the analog level to a digital count. It's already an oscillating circuit. So if you replace this oscillator, I want you to compare this implementation with something which we are suggesting here. It's a single device put in series with a resistor and a capacitor. This is a much simpler circuit, and this also performs the oscillator action, temperature dependent oscillator action. And so let's start with the device first. So this is the stack shown here. So there is an SiO2 substrate. The SiO2 is just for the isolation, then a Ti layer for adhesion, followed by an MSM structure. So this PMO, this oxide is a semiconducting material, and it is generally used for RM devices. But here, what we find in the DC characteristic of this stack here is that there is a sharp shoot up in the current. So this current is highly non-linear, and in addition to the non-linearity, there is a hysteresis. So within one arm of, let's say, the low resistance state of this RM device, within that one arm, what we see here is that there is a switching behavior and there is an hysteresis. So whenever we have these kinds of characteristics, they can be used in an oscillator circuit. And to characterize these thresholds and how does this hysteresis window vary, we did a current sweep, and we increased the current, and we found that these kinks correspond to those voltage values at which these resistance switch is observed. And if we plot these thresholds against the ambient temperature, we find that this hysteresis window reduces. And after let's say 380 kelvins, we don't find any hysteresis window, and the oscillations will stop. So this will define the range of operation of the temperature sensor. And it is because of this change in the hysteresis window that we can change the output frequency. So let's look at the circuit to make it more clear. So this is the device whose characteristics were shown on the last slide. And so on this graph, I am showing two thresholds, which are the resistance switching thresholds of that device. And by choosing a resistor value in series with this PMO, I can decide the steady state values of operation of this circuit such that the thresholds lie completely inside the steady state windows. So this is the key method which is used to make such circuits oscillate, the hysteresis thing. So whenever you apply a constant pulse here, input bias, and the circuit tries to reach one of the steady states, but before it hits the steady state, it hits the threshold, and the steady state itself changes. So by keeping the window within the steady state, it keeps on oscillating forever as long as you apply the bias here. And now, so these are the experimental transient oscillations you see. the variation of one of the thresholds which we saw earlier is what you see here. So earlier the amplitude was high, and now the amplitude is lowering because the amplitude is decided by this VH and VL difference, the difference between the switching thresholds. However, when the amplitude is changing, the discharging and charging rates are not changing because these resistance values are fixed. The temperature only changes the thresholds in the bias, and that is why we, with reducing amplitude, we see an increase in the oscillation frequency. And this is the kind of curve we see for the this circuit, and the frequency versus the temperature. So this varies from like room temperatures to about 80 degrees range above that. And so in order to use this device in a circuit and actually create a digital count out of it versus temperature, we did Verilog-A modeling. So we created a behavioral model of the device. We captured only the specific aspects which are, so there is a hysteresis window, there are switching thresholds, and once it is in one resistance state, we model it as a simple ohmic device. So these are pure resistances. And we see that this kind of a behavioral model is sufficient to capture the oscillation characteristics of the experimental oscillations so this is the comparison. And similarly, the frequency versus temperature of the simulations also match well with the experiments. So this kind of model is what we'll henceforth use to characterize the frequency versus temperature in a circuit scheme in which you like convert the frequency directly to digital counts. So this part of the circuit is not new, which is connected in taking the output of my temperature sensor. So what it does, it simply removes any DC bias, removes any noisy behavior which could lead to additional digital counts which are not because of the temperature but noisy variations. So it filters out those components, and we sample it for some clock period, and we get the digital count output here. So this is what I have shown here. Starting from the oscillations, we reach the digital count, and as the oscillation frequency increases, the total count output in a particular fixed period of time also increases. So this is the simple frequency to digital converter circuit, and here we have extracted the frequency information from the other features of the transients which are not so important. And so one thing I would like to highlight here is that so these devices being non-silicon PMO based, novel material based devices, there is a slight amount of device to device variability. So for example, you have two separate PMO stacks and they are showing me the same digital count, but we can expect an error of 2 degrees Celsius between them, and that is what we have plotted here. But the cycle to cycle variability, now for a fixed PMO device, the variability is much lesser, and that error is only about 0.5 degrees Celsius. So to conclude my talk, I'll say that we have demonstrated a self-heating based. So actually, so this PMO, this sharp switch which you saw is because of the self-heating itself in PMO. It is very thermally insulating material as compared to silicon, and that is what causes this non-linearity which we see. So this is a self-heating based device. It's a non-silicon device, but the circuit we saw can be much more compact than the conventional ring oscillators. And then we used a behavioral model to get the frequency output characteristics versus different temperatures. And what we intend to do with a simplified circuit and a compact circuit is, consider in a region of space where you need an exact temperature map of some electronic circuit. So where you require a very high amount of spatial resolutions between adjacent positions having different temperatures. For example, on a motherboard, there are different chips having different temperature profile. We would want to have a compact temperature sensor which could actually pinpoint the temperature of a particular region. So that's the motivation behind the compact thing. So that's it for my talk. Thank you for listening.